Hi everybody. Today I am going to discuss about square isolated footing. Here this is the column size. Let's take this laser points. So this is the column size and it is the load applied P. It is load applied on the column. At an end it reaches up to the footing. And P. It is combined value for the service dead load and the service live load, and the dead load and live load 1600 kilonewton, 1000 kilonewton, totally it is coming to 1600 kilonewton. So this is the force 2600 kilonewton. It will be applied on footing through the column. So let's move ahead to see how we can handle this load to analyze the footing. First, our concentration on allowable net soil pressure. It is Qn equal to 260 kPa. Our next step to find the area required. How to get that? P divided by Qn. So what's the value for the P? It is 2600 kilonewton. As we have seen in the previous slide, it is 1600 kilonewton, 1000 kilonewton, adding this 2600 kilonewton. This is that, divided by 260 and this one. We got 10 meters square. If we do square root, it gives us 3.16 meters square. It means footing size 3.16 by 3.16 meter, but we have to take some round figure, say it is 3.250 millimeter by 750 millimeter thick. We are assuming this value right now. Later it will be changed if it is needed. And from these points, like 3250 millimeter square, we have to find the factored net soil pressure. So how to get that? In this case, this 1600 to be multiplied by 1.25 factor and this live load to be multiplied by 1.5 factor and divided by the area of the footing. It is 3.25 by 3.25. So our factored net soil pressure will be 331 kPa. And this pressure we will use in next slides. So let's move ahead. If we look at the footing, in the section it is showing there is a two cracks on both sides of the column, incline crack. And this incline crack, basically it is up to D, I mean depth of footing. But we are considering to find our tributary area for two-way shear, we are considering it is D by 2 distance. That's why this hashed area, it is the tributary area for two-way shear. And if column size is C, then taking D by 2 on both sides of column, we get this length C plus D, this length also C plus D. One important thing I want to tell, generally thickness of a square isolated footing, it is governed by two-way shear. These very important points. And these two-way shear, and in another name is their punching shear, it is a measure of diagonal tension caused by the effect of column loads on footing. Already we have seen here this inclined crack. It shows us how diagonal tension actually impacting on the column, on the footing. And the compression load from the column spread out into the footing, opposing diagonal tension at a distance d by 2 from the face of column on all sides, with a result that a square column tends to punch out part of the footing. It's very clear now which part is punching out, this part. If you look at inside area of this inclined crack, it is showing this area due to the load from the column, part of this footing punching out. So concept is like this. That is why you call it as two-way shear or punching shear. Now we have to take average depth, because before we assume depth is 750, but in really if we want to get the D, it will be different than what we assume, because we have to subtract this cover under this steel as well as average dia of the bar we have to subtract, so it will come 650 millimeters. Then need to find the length of critical shear perimeter B0. Critical shear perimeter, it will be this perimeter, this red line what I have showed here, because outside all this hashed area, it is the tributary area for two-way shear. So what is that B0? It will be nothing but 4 multiplied by C plus D. So it is 4200 millimeters. Now we need to calculate VF, applied shear force at section due to factored loads. This is VF. So 3.25, this 3.25 minus of 1.05, 1.05. It's very clear. 3.25, 3.25, it means it is outside this, whole footing area. 3.25, 3.25 minus 1.05, 1.05 means we are subtracting this part, C plus D by C plus D, this area we are subtracting. Then we are multiplying it by 331 kPa. So we are getting applied shear force at section due to factored load 3131 kilonewton. Already we know wave reinforcement is rarely used in footing. And we calculated before, in the previous slide it was VF. Now we are calculating factored shear resistance of a section, that is VR. It will be small VC B0D. So this VC, factored shear stress. It is factored shear stress. It's very important points. Factored shear stress, we have to calculate that, but we will use three equations. So out of those three equations, which equation gives us the least value, we will use that one to find this VR. It is very important point too to understand. This VC will be calculated by three equations. And out of those three results, we will check which one gives the minimum value. That VC we will use it here. And this VC, I am telling again, it is factored shear stress resistance provided by concrete. As I told, the small VC is the smallest of, this is one equation. We will use another two equation in the next slides. So let's see first with this equation, what is the value comes. So already I told VC is the smallest of this A. So we have to put the value for beta C, it is 1. And once we put this value as well, other parameters, this lambda phi C, square root of FC, we get VR or VC. It is factored shear resistance, factor shear stress. This VR or VC, factor shear stress resistance, both are same. It is 1.80 MPa. Let's see in the next slide with other two equations. So we are now in the second equation. Already we got this first one. Now we are in the second equation. We have to use the value for alpha S. It is equal to 4 for an interior column, as well other parameters. In the same way, we have to put the value for lambda phi C square root of F prime C, and we get the equation VR or VC, it is equal to 2.46 MPa. So factored shear stress resistance provided by concrete, it is equal to 2.46 megapascals MPa. So let's see in the third equations, what it is. So already we checked the first one, second one already we saw. Now we are with the third one. Let's put the parameters value 0.4, lambda equal to 1, phi c equal to 0.6, and square root of 25, we got 1.20 MPa. So it's very clear which one gives the smallest one, number C. So 1 we got, 2 we got, 3 we got. Now we'll choose the smallest VR equal 1.20 MPa. Now we'll use that equation VR. VR, factored shear resistance of a section. So to find this VR, factored shear resistance of a section, we will use this VR 1.2 and other will be as it is B0D, already we know 4200, D is 650. So we got 3131 kilonewtons VF. Applied shear force at section due to factored load, this is VF. Applied shear force at section due to factored load, we got 3131. Now VR 3276, we got VR 3276, factor shear resistance of a section VR, and VF applied shear force at section due to factored load, this is 3131. Comparing these two, we found VR greater than VF. Easily we can say the depth D is okay for two-way shear. So we assume depth 650, that is perfect because VR greater than VF. So this is the end of our two-way shear checking. Now we will see in the next slide one-way shear. This hashed area, it will be at a distance D from the face of the column. And here it is showed that the cracks, as I told before, these cracks and it is at a distance D. And tributary area, it is smaller, not that much big like two-way shear. It was a very big area. Now for one-way shear, small area, but we need to find this B1. So let's see how to get that. As I mentioned, one-way shear is located at a distance D from the face of the column. So we need to find D equal to how much? 650, already we know. QFN 331 kPa, we have seen in previous slide. L 3250, we know that. So we need to find B1, this one, B1. So once we get B1, it is easy to calculate what is VF. QFN L B1. Using all this, we find 834 kilonewton. Applied shear force at section due to factored load, and it is one-way shear. Applied shear force at section due to factored load. We will use this equation VC or VR. It is shear force resistance by concrete. Shear force resistance by concrete, this is the equation or formula. We have to use this to find this value VC or VR. What will be that? Just putting the value of lambda, phi c, already we know. F prime c, B, W, D, all we have. So once we put this value, we get, so we put all the values. So what we will get? By calculator, we get VR equal to 998.998,636. It means 998 kilonewton. Because it was Newton, we divided by 1000, so it got 998 kilonewton. So what you can say? VR greater than VF, because in the previous slides we had value for VF, and VR, it is far greater than that value. So this both I mentioned here, highlighting this. So VR greater than VF, so it means depth D is okay for one-way shear. So one-way shear is done. Now we need to check flexural action of an isolated footing. It is at the face of the column. Before we did D by 2 distance, D distance, but here for moment, always we do at the face of the column. That is why it is written moment about axis AA at the face of the column. And tributary area is this one. And this distance, it is B. Resultant of the soil pressure, QFN L into B. This is L, this is B. So if we multiply L into B by QFN, we get QFN 331, already you have seen in previous slide, and 3.25, it is the length, and this value of B, it is 1.425. So resultant of soil pressure, it is 1533 kilonewton. It is working here, exactly here, in the center of this width. That is why it is shown here. It is shown here B by 2, the distance from the resultant to section AA. So if we want to get the moments, so surely this value to be multiplied by this distance. That is why it is shown here QFLB into B by 2. This one. QFN LB multiplied by B by 2. So we know this value, so it is easy to find this. So MF, applied moment at section due to factored load. This is MF, applied moment at section due to factored load. This moment we got 1092 kilonewton meter, and using this moment we will find the amount of steel or amount of reinforcement needed for this footing. Another important thing is I checked on this side, as it is a square footing, other side also it will be same. So it is not needed to check other side because it is same. So let's ahead. In the next slide, we have to use this MF 1092 kilonewton meters. We will use our formula This MF equal to this, so AS equal to MF by phi S Fy Ze. Just need to put the value for all these parameters. 1092 10 to the power 6, this one, it was kilonewton meter, we put it Newton millimeter, and this phi S 0.85, Fy 400, J 0.9, and D equal to 650. We get AS equal to 5940 millimeter square. Another important thing, we have to find also steel amount minimum. There is a requirement by code 0.002 AG. 0.002, this is the area of the section. 3250 multiplied by 750, we found 4875 millimeter square. So looking these two values, 5940, this is 4875, this one higher than this, that's why does not govern. So according to this value, we have to take round figure, says 6000 millimeter square. It is equal to 12 numbers 25 bar. 12 numbers 25 bar. So this is 6000 millimeter square. Now here there is an important checking. It is very important because we got the number of steel, but that is not the final, because we have to verify it. Is it the failure, the way, mode of failure, is it acceptable or not? Because there is a concrete failure, there is a reinforcement failure. Which one comes? We need to check. So we'll check with the balance failure. So here what we will do, we will find the value for A. A is the depth of equivalent rectangular stress block. Depth of equivalent rectangular stress block depth is, it is A. So we have to put all these values, I mean parameters, what it is here, like phi S, phi C, AS, Fy, alpha 1, F prime C, B. But we need to find alpha 1, how to, using this equation as it is given by the code. So we find this alpha 1 value 0.183, 0.813. So phi S, phi C we know 0.85, 0.6. AS already we got here 6000, Fy you know 400. This alpha 1 we got 0.813. So here we found fast. Then we use this formula. Then I find this 0.813. Now we are putting all these values. So it's very clear now. It looks very clear right now. So 25.813 multiplied by what? F prime C, it is 25, this grade of concrete, and 3250, this is the size of the footing, length or width, it is same. So what you got? 51.47. Now we need to find the ratio of this A by D. It is very important to check. So A by D means 51.47 divided by 650.079. Now we need to compare the same ratio for the balanced failure. So what is that? For this we have to find beta 1. Using this equation we found 0.908, and AB sub B divided by D. This is also A, it is also called actually depth of equivalent rectangular stress block, but on balanced failure. That is why it is A, but sub is B, balanced failure, divided by D. We have to use this formula. as per code suggests this one. So AB by D 0.908 and this 700, 400, I mean 700, this FY 400. So A by B, AB by D, we got 0.578. Now we can compare this. So let's see one by one. First we got this, then we got this, then I got 0.578. So this value of 0.79, it is much smaller than 0.578. It is written Fs equal to Fy. It means there will be steel failure, which we are intending to get that, because we don't want concrete failure, we want steel failure. It is safer. So let's move in the next slide to see. Therefore, steel would yield at failure. What I have said in the previous slide at the end, steel would yield at failure. That was our requirements. Now we have to find factored moment resistance of a section. Factored moment resistance of a section. So what we'll do? We'll use this equation, factored moment resistance of a section. All the parameters we'll use 0.85, 400, 6000, all we know already got in previous slides. And then we have this 1273, that is the value we got, 1273 kilonewton meters. kilonewton meter. This MR, it is factored moment resistance of a section. Now considerably larger, because our MF, it was 1092 kilonewton meter. MF, applied moment at section due to factored load, it was 1092. But factored moment resistance, we got 1273 kilonewton meter. So this MR, it is greater than MF. Why not we try with less number of steel? Before we took 12. Now we try with 11 number 25 bar. So in this situation, if we use 11 number 25 bar, what will be factored moment resistance? Let's calculate that. And it is 1166 kilonewton meter. Still it is greater than MF. So we are okay, because still MR greater than MF. So we can use 11 number 25 bar each way, each directions on the footing. So it is perfect to use this. So what we found? 11 number 25 bar each way. That's all for today. Thanks for watching.